In this video, we are going to introduce the topic of chemical equilibrium. There's three main learning objectives that we're going to talk about in this lecture video. The first is going to be a basic discussion of the difference between static and dynamic equilibria. Of course, in our everyday conversation, we might hear and oftentimes use the word equilibrium, and there's some very important distinctions between the different types of equilibrium we might be referencing, and we'll find that it's actually this concept of dynamic equilibrium that we really need for our discussion of chemical equilibrium. Next, what we're going to do is describe the nature of equilibrium systems. I want to take us from a macroscopic down to a microscopic view to really appreciate the chemical equilibria at all these levels. And finally, we're going to explain the dynamic nature of chemical equilibrium itself, again, looking at both a macroscopic and microscopic viewpoint. Okay, so to kick things off, let's make clear what we're talking about when we describe equilibrium in terms of either dynamic or static. You may have heard the term, again, equilibrium. You might have used the term. Oftentimes, equilibrium refers to a state of physical balance. And so our nice little picture here on the left-hand side showing these balls in a little plane, delicately balanced as such, is an example of a static equilibrium. And of course, this isn't a very stable equilibrium. You can imagine perturbing or hitting one or even slightly touching one part of this system, and the whole thing is going to fall apart. Nevertheless, the fact that this system is stationary, that these pieces aren't moving around, this refers to static, lack of motion in that equilibrium. Now, I want to compare that to what we would call a dynamic equilibrium. And to build up the concept of a dynamic equilibrium, I want to draw upon a cute little analogy here involving a beach setting where you could imagine some beach goers here shown in gold that are hanging out in the sand enjoying the sun, and some beach goers here shown in blue that are over here out there in the water splashing around and enjoying the water. Now, what I want to consider is the ratio. So I'm going to set up a ratio here. We'll put on the top, we could consider the number of beachgoers that are being shown in blue here being out in the water. And we could consider the number of beachgoers shown in gold here. Gold that I'm looking for, but there we go. That might be a little closer, maybe not. Either way, we've got our ratio here of folks that are hanging out in the water and folks that are hanging out here in the sand. Okay, so you could imagine at any point in time throughout the day, throughout a given hour, you could take a snapshot photo of that beach scene here and count up all the number in each one of these categories and set up a ratio. Now, of course, if someone's hanging out on the sand, they're not likely to just stay on the beach the whole day. They're going to get warm from hanging out in the sun. They're going to want to go get in the water and cool off. Similarly, folks that are out here in the water swimming around are eventually going to get tired. They're going to come back and hang out on the beach for a bit. And so on and so forth. So this sort of back and forth of going into the water, out of the water, back onto the sand is going to happen. For any given beachgoer, they're constantly going to be going back and forth. And of course, for a given person, the rate's going to differ. But what I want to consider is the aggregate total. And we could imagine a dynamic equilibrium being established in this scenario if for every time an individual that's on the sand they go into the water, another individual in the water comes back onto the sand. Right? So if that happens, right, if you have a really packed beach, there's so many people out there, every time someone goes into the water, somebody else comes out of the water, and vice versa, then you could imagine that this ratio down here is going to remain fixed. Okay? The total number of people in the water or on the sand isn't changing. Okay? Even though individual people are going in and out of the water, the total number for a given snapshot is remaining fixed. If you achieve a scenario such as this, we have established what we would call a dynamic equilibrium. Number of people on the sand or in the shore will remain constant. Okay, Now, let's consider what would happen if we somehow change this system, right? And let's say that the sun goes down, for example. If the sun goes down, there's obviously going to be changes in the people's behavior. For example, we could imagine seeing a shark fin out here in the water. Okay, if a shark fin shows up out in the water, then presumably a bunch of these people that are hanging out there in that ocean are going to see that shark fin. They're going to run back onto land, and as a result, we would be shifting this ratio. We would be changing the relative numbers of people on the shore and in the water. And of course, once everyone's acclimated to that new change, for example, a shark is there, then almost everyone is going to be over here on the shore, you'd imagine. And maybe there's just a couple people, the folks that like swimming with sharks, maybe studying them or who knows what. Those folks are going to be the only ones in the water. And then at that point, we could imagine developing a new dynamic equilibrium involving only the people that would want to be out there with those sharks. Okay, so a silly little analogy here, but if you can understand this little picture here, then you can actually go a long ways into understanding what's going on with molecules, right? And so what I want to now do is focus in on a chemical system, right? And it's going to be a very simple chemical system, as easy as basically a two-state thing, just like we have here in the water, out of the water. We're going to imagine two different molecules being present, and we're going to observe how the ratio of those molecules being present can change over time. We can establish an equilibrium with those relative amounts of molecules, and how we can change those relative amounts. All right, and so to do that, what we want to look at is a special type of reaction that we call a reversible reaction. Right? And so a reversible reaction, simply put, is a reaction that can proceed in both the forward, that's going to left to right section from position. Sorry about that. Reactants to products, and the reverse reaction going from the right back to the left. Right? So if you have a reaction that can go in both directions, then you have what we call a reversible reaction. So a nice example of this is a reaction called N2O4, or a compound N2O4 that we know decomposes into two molecules of NO2. Right? And this is something that will occur in the gas phase. Right? And so this reaction goes back and forth, just like we saw with the people going into the water, out of the water, into the water, out of the water on that beach scene. All right. And so what I want to do now is flip over to a video here that's going to illustrate this molecular reaction at a macroscopic level, actually looking at test tubes that contain these gases. Okay, so here's a depiction of a little laboratory setup where we are showing NO2 on the left-hand side in our chemical reaction equation, which has this red-brown color. And if you look at the test tubes on the left and right-hand side of the frame here of this video, we see that both of these test tubes are characterized by this red-brown color, meaning that there's a whole bunch of NO2 gas molecules present in these tubes. Now, we know, according to the reaction equation I just wrote out on the previous slide, and we've got shown here in the video, that these NO2 molecules can come together in this reversible reaction to form N2O4. And it turns out that when those two NO2 molecules come together and to form N2O4, they actually also release heat. Okay, so what we're going to find as we play the video
exothermic
is what
reaction.
happens when we place
We're going to use Le Chatelier's principle to predict the shift of the reaction with respect to temperature and also the color.
Cold water bath
because this reaction is exothermic, heat is a product.
Right. So our
Therefore,
laboratory personnel,
adding more heat to the reaction
here is going to go ahead and place
will shift it towards the red-brown reactants, the NO2.
Establish a nice dark red-brown color.
Placing the other tube in cold water is the same as removing heat from the reaction, so removing a product. That will result in the conversion of NO2 to the colorless N2O4.
The color starts to shift to be less red-brown, right? And a distinctly cooler color. And so what I want to point out here is that over time, this light brown color that is established on the right-hand side, the color is changing at first, but then an equilibrium is established once the molecules in this reaction is adjusted to this change in the temperature of the surroundings. And the color changes, it gets lighter, but then it stops changing, and you establish this new equilibrium characterized by a lighter shade of brown, right? And so what this is an example of, basically going back and forth here. Watch it one more
Placing
time.
the other tube in cold water
This is
the same as removing heat from the reaction, so removing a product.
Back and forth,
that will result in the conversion
that
of NO2 to the colorless N2O4.
Environmental conditions. Okay, what I want to do now is zoom in and start looking at the molecular level. So if we consider that exact same reaction we had on the video, and we say, for example, let's suppose we could start off with entirely N2O4 molecules. Nothing is decomposed. So we could imagine a completely clear test tube comprised at the molecular level of entirely N2O4 molecules. Now, as soon as we let this reaction go, or we heat up this reaction just a little bit, and we put some thermal energy in there, say bring it to room temperature, what have you, then we are immediately going to see the decomposition of this N2O4 to start forming NO2 molecules. So after some amount of time, you will start seeing fewer and fewer of these N2O4 molecules and more of these NO2 molecules. All right, and as that occurs, we will start seeing a darkening of our test tube. Right, at the macroscopic scale, you start to see the properties of the macroscopic aggregate of NO2 molecules that have this red-brown color. And of course, the color is going to keep changing. It's going to keep getting darker until we establish a new equilibrium, until the rate at which molecules of N2O4 are being broken down into NO2 equals the rate at which molecules of NO2 are coming together to reform N2O4. So just as we saw with the beach analogy, when the ratio remains constant, when the rate at which people are getting into the water and out of the water is equal, then we've established an equilibrium. So the same sort of thing is going on here with a reversible N2O4 reaction. Okay, so to just highlight these points, right, we're stepping through initially all N2O4 is present. As time progresses, N2O4 is converted, but we are not at equilibrium yet, right? There will be this phase where you're going from the initial start of that reaction. We have to step through before we reach equilibrium. So at this intermediate stage, right, we're only partway there. And then, of course, anytime you have NO2 present, as soon as you get the first two molecules of NO2 present, you will start having that reverse reaction where the molecules of NO2 can start going back to form N2O4. And of course, right, as I said, once the rates of this forward reaction and reverse reaction are equal, you're breaking down and building up N2O4 at the same rate. That's when you reach this equilibrium, and that's when you will no longer see color change in this chemical reaction too. And so that brings us to our definition here of chemical equilibrium. So chemical reaction is said to be at equilibrium when the rates of the forward and reverse reactions are equal, okay? So the key words here are rates are equal, and therefore the concentrations of product species remain constant. So I'm going to highlight these terms because this is a very common misconception, right? When we are saying it's the rates that are equal, right, and the concentrations are constant. Okay, so a common misconception that I will see students bring to this concept is thinking that at equilibrium, concentrations must be equal. That's not the case at all. As you could see here in this example, at equilibrium, right, we have way more NO2 molecules present, and we have a distinct brown color. There's more NO2 molecules present. So the concentrations aren't the same, but the rates at which the molecules are going back and forth between NO2 and N2O4, that rate is equal. And because the rates are equal, the concentrations, they're not equal, but they are constant in time. And so that's what we mean when we say chemical equilibria are dynamic. We are seeing equal rates, constant concentrations, but individual molecules are constantly reacting and going back and forth, decomposing, forming, decomposing, forming. Again, just like those individuals, beachgoers are constantly going into the water, out of the water, into the water, out of the water. Motion is always occurring when you're dealing with molecules. All right, so let's look at this from an alternative standpoint, bringing in a little bit more on the mathematical side, using our prior knowledge regarding rates of chemical reactions. And let's look at some figures that are going to allow us to plot concentrations as a function of time and understand in yet another way what's going on here with chemical equilibria. So on our previous example, what we started off with, which was a whole bunch of N2O4. Right? So our concentration as a function of time for this chemical reaction here, right, is basically starting off and say, hey, at time equals 0, we have everything is N2O4, right? And so there's 0 concentration down here of NO2, right? And so this is where we have our completely clear little reaction file. As soon as N2O4 starts decomposing, the concentration of N2O4 is coming down. Makes sense. And as soon as you decompose N2O4, you start to form NO2, right? You get, of course, twice as many NO2s for every N2O4 molecule that you decompose. Okay, so it makes sense then that we have a decreasing concentration plot for N2O4 and an increasing concentration plot for NO2. Now, I also want to point out that these changes are not linear. Right? And hopefully this makes sense because, right, if as soon as we break down N2O4, it's not just, monotonic breakdown of N2O4, and that's describing what the concentration is going to be. We actually see, I should say, it's not just a linear breakdown of N2O4 and a linear decrease in concentration. Right? What's happening as soon as you break down N2O4 and you start forming even the smallest amount of NO2, then you start seeing this reverse reaction taking place, right? And so that complicates the mathematics, right? And we're going to be exploring the details of the mathematics in future lectures to come. But for right now, what I want you to do is just think back and remember, when we are dealing with elementary reactions, right? And we're dealing with the elementary reactions of either the forward or reverse reaction here for our N2O4 decomposition reaction, we could write down the rates using what we know from rate laws. The forward reaction is going to be some rate constant, Kf, F, of course, denoting forward reaction, multiplied by the concentration of that reactant, N2O4 in this case. The rate of the reverse reaction, similarly, will be some rate constant, defined as Kr for the reverse reaction, multiplied by the concentration of the product, raised to that stoichiometric coefficient. Again, because we're talking about elementary reactions here, right? So we can then think in terms of rates of reactions, and we can, of course, it's not surprising then to find that the rate of the forward reaction will, of course, be decreasing as we decrease the concentration of N2O4. The rate of the forward reaction will be increasing because we are, of course, increasing the concentration of NO2 as we're decomposing N2O4 and getting more, a higher concentration right here. So the rate of the forward goes down, rate of the reverse goes up. However, once you reach a certain spot, right here, denoted by the dashed line, and this would be the same point in time on both of these plots, be the same point, right? What we are seeing is that after this point in time, concentrations are no longer changing. We're seeing these flat lines here in the concentration, and the rates of both the forward and reverse reactions are equal. right? And of course, this is what we call equilibrium, chemical equilibrium, right? So once again, once you're over here in this chemical equilibrium portion, the concentrations need not be the same. In fact, it would be very rare to find a reaction where you have equal concentrations of reactants and products. It's a very rare thing to think about. In general, you're going to have very different concentrations of the reactants and products, but at equilibrium, their concentrations stay the same, but the rates of the forward and reverse reactants remain constant, right like so. Okay, so let's sum up what we just talked about here one last time to wrap up our introduction to chemical equilibria. So we've seen from multiple perspectives now this concept that chemical equilibria are dynamic. Molecules are constantly moving around, reacting, forming products. Products are coming back and reforming reactants. Okay, so very important. The reaction has not stopped at equilibrium. Reaction is always happening. The molecules of N2O4 constantly decomposing into NO2 molecules are constantly combining. Now, the characteristic of equilibrium is going to be a rate of decomposition being equal to the rate of formation, seeing reaction rates becoming equal. Concentrations remain fixed, static, but reaction rates remain equal.